So for our second talk this morning, we're pleased to have Masahito Yamazaki, who will talk about 3D n equals 4 theories, Quiver varieties, and vertex operator algebras.
Okay, let's see, is the microphone on? I think it's on. Maybe I should make it closer. Is it better now? Or maybe not, so. Well, let's see, why is that? Right in the middle, center, okay. Here. Okay, is that better? Somehow it feels it's not the best, but hope everybody can hear. Okay, good. So please let me know if you don't hear anything. Also, yeah, this time I'm very tempted to use the blackboard. Well, this is a party meeting of mathematicians, and so I'm very tempted to use this actually very beautiful blackboard. And of course, let me thank the talk by thanking the organizers. And actually, just like Amina, I came to ICTP as a graduate student. In fact, it was one of my first trip to Europe as a graduate student. And ever since I've been here, and also to Trieste many times, it's always a pleasure to be back. Now, so this is a conference about mathematical physics, right? So it's an interaction between mathematics and physics. Sometimes the development in mathematics motivates the development in physics and vice versa. But it's actually also true that sometimes, for example, through physics, different branches of mathematics are connected. And so actually, even from a purely mathematical viewpoint, the interaction is pretty useful, and vice versa. And that's the general theme of my talk. And that's reflected in the title. So this talk is about 3D n equals 4 theories and the relation between Quiver varieties and vertex operator algebra. So Quiver varieties, vertex operator algebras, they're mathematical well-defined concepts. But we're going to see that there is a very nice parallel in between them. And we're going to extract new information from there. And this work is in collaboration with my excellent collaborators, Iwano Koman, Myunbo Sim, and Ihao Tso, who are or used to be the postdoc at my institute. And the one thing to note is that this is based on a paper which appeared last December in physics. But actually, the physics paper contains some theorems and statements. And also, we are preparing yet another paper in pure math. So hopefully, depending on preference, you can have a look at either of them and try to enjoy it. Yeah, so let's see. So let me today begin with the first general introduction. And well, let me first start with the Quiver Q. I try to write reasonably large. So, or maybe this is too large. So Quiver is just vertex and edges, just in case. Let's see. And then also we associate the dimension vector B and W. So I just saved a little bit of time by drawing a board. So we have nodes. This is the Quiver, but there are also frame nodes, which are represented by squares, which is the standard notations. And you associate the numbers, dimension vectors, B and W. So that's Nakajima's notation. And so this is the defining data. So I keep using Q, B, and W. And this data is the defining data for three-dimensional n equal 4 gauge theory, if you're a physicist, gauge theory. And well, this data is Q naught, the vertices is like n equal 4 vector multiplet. So it's represent the gauge group. So the gauge group is like a product of, say, if it's SUN or UN, let's say UN BI. Does it look okay? Yeah. Okay, I think it's okay. And then there's a Q1. So this is edges, arrows. So this is n equal 4 hypermultiplet. And then there are arrows, and I'm sure that a lot of people have seen this already. But if there are arrows in between, for example, it's in the bifundamental representation. So okay, it's a standard definition of the Quiver gauge theory. And then one nice thing about it is that once you have this theory, it's a physical theory, but you can extract different mathematical ingredients. So one is one such thing. Okay, maybe let me write it here. One such thing is the Quiver variety, Nakajima Quiver variety. Okay, so what is it? Well, Nakajima Quiver variety in the physics language is the Higgs branch of the moduli space, vacuum moduli space. Let me write M Higgs, and I'm going to write it as MQBW. I'm going to define it later. And then on the other hand, there is also a different concept, which is the vertex operator algebra. And it goes by the name H over A twisted vertex operator algebra. boundary vertex operator algebra. So I'm going to denote it by B of the dimension vector, Q and dimension vector. Okay, so how to extract this? Well, the basic idea is to go to the boundary. So this is a three-dimensional theory, and you can try to go to the boundary. But first of all, this is three-dimensional four supersymmetry. You have to specify what boundary conditions you talk about. You choose. You preserve the boundary condition, which is half, 0-4 supersymmetry, etc. But the details doesn't matter for the purposes of my talk. It's just that you have a 3D theory, and on the boundary you have a 2D, which is described by this BOA. And now there are two different types of boundary conditions. Well, actually there are more, but two different types of boundary conditions, which are called A and B type. A and B, as you are familiar with the mirror symmetry, and I'm going to consider the A type. The previous talk is actually with the Coulomb branch, which is the other B type boundary condition. But in this talk, I'm going to consider A type / Higgs type boundary condition. And then the statement that you get on non-trivial BOA starting from this 3D equal 4 theory. Now, well, let's see. So this is enough, but another way of saying that is that if you start with 3D equal 4 theory, so this is a physical theory with a gauge coupling constant, etc. But you can also go to 3D theory, 3D TQFT, by the topological twist. This is, well, let's see, again, there is A twist, B twist, but let's say A twisted TQFT. And once you have the TQFT, you can also go to the boundary. So, and then that's how you get a BOA. So this is like a generalization of the celebrated correspondence between Chern-Simons and Western model on the boundary. But it's a more involved one. This 3D TQFT, for example, partly because this thing contains many extra matters, scalar fields. So it's not, for example, pure Chern-Simons, but more things. And in particular, contains local operators. And that means that there is an even richer structure on the line operators, point-like defect inside the line operator. So there are even higher categorical structures and non-semi-simple TQFT, etc. There are a lot of structures. So if you're interested in knot theory, etc., this is what is underlying here. Although I'm not really going to talk about 3D TQFT, but just concentrate on this particular BOA. Now the question is that the natural question, if you look at this picture, is that what is the relation between, first of all, what is this BOA? I just wrote it abstractly as BOA. Is there a procedure to specify it? And also, can you identify it? Like what are the generators or central charge or et cetera, et cetera. So that's a very concrete question. And in fact, that question has been addressed. I should say that, so this is the Blackboard talk, so I apologize, I'm not going to list that many references, in fact, very few references to save time. But at least I should say that this type of discussion is initiated by Costello and Gatto, Kevin and Davide, and there are many people who have worked on this. In particular, Thomas Kreutzig, Tudo Di Mofte, Nick Garner, and many other people. Sorry, I don't name everybody. But let's see. And so it's an interesting subject on its own. And so far, most of the development happens for abelian gauge series. But I'm going to, what my interest is partly about trying to understand the connection to Quiver varieties, general Quiver varieties. So I want to go to the non-abelian case and then discuss the associated BOA. Now, one question is, of course, how to understand this. But there is another question as to how to understand the relation between the two. Right, so it sounds like a natural question. Well, a priori, there are different objects, but it turns out that there is a very close relation. So the motto is that if you start with a Quiver variety, you can chiralize. So make it holomorphic, and then you get this A and H twisted boundary condition. Although with a lot of subtleties, actually. So in fact, clarifying that it's, but at least the motto is that you kind of uplift it, and you get a BOA. So Quiver variety uplifted as a BOA. Now you can also try to go the other way around, and that's also a very subtle story. And part of our interest is to try to prove the statements. But at least at the zeroth order, there is a concept of associated variety. Associated variety. And if I have time, I might comment just a little bit on this. But there is the statement is that you have a BOA, there is an associated variety. There's some variety, geometry. And then so, roughly speaking, if you start from here, and then you can go extract the geometry and then go back there. that's one definition of colorization. So the goal of my talk is to try to understand first the relation between the two. And I'm going to explain the story, in particular this construction of BOA, in such a way that the parallel with this is extremely clear. And then I'm going to study this BOA itself, and in particular, connection to the W-algebras, and free field realizations, or Miura transformation, if you like, free field realizations. So that's what I'm going to talk about. Okay, hope these things are clear. Okay, now let's try to discuss the first Quiver variety side. Now, I'm sure that many people have seen the definition of Quiver varieties, and I'm going to comment very little about that. Only the minimal ingredients needed. So, okay, so let's come to the Quiver variety. So, okay, so what are the Quiver varieties? Well, it's defined by hyperkiller quotient of something by some group action. So you need to first show what are the starting object. And the starting object I might write as a lep of the Quiver, QBW. Okay, so what is the, so you regard the Quiver as the set of collection of vector spaces located at each point. So here I have a little bit more messy figure. So if you have V1, you have, for example, here you have V2, and you have a vector space of the V2 with dimension small v2. And you have the, again, similarly, the vector space. And then, of course, these arrows are morphism. It's in between. And in particular here, there is a notation. So there are arrows between different vertices. And the arrows coming to the right I call X, Y called Y. And there are also arrows coming from the squares, framing nodes. That's denoted by alpha and beta. So these are the data. So roughly speaking, these are like alpha xi, yi, and okay, so I already capitalized it. Okay, xi, yi, which is not a good notation, but okay, alpha beta I. And then, yeah, so the collection of these. These are just a cotangent of lip. That's what I mean by that. So it's just a collection of matrices, if you like. Now, there's action of the GLB, what I like GLB. So this is the complex equation of the gauge group, GLBI, I at the associated vertices. And so it acts on the space by conjugation by matrices, of course. And then there is a concept of the moment map. There is an ice moment map associated with this action. And this takes the form of xyi minus yi minus 1, xi minus 1, plus alpha I beta I. So you can check that, for example, xiyi, let's see, xiyi, so that first goes to, oh, sorry, this index was wrong, yi, and come back, for example. So if you're starting with that vertex, you can go around. There are three ways of going around, and they all appear inside this moment map. And then once you have this moment map, I think you can see even when right here. And then there is a quotient. So that's defined. So that's the definition of the Quiver variety. So this is M, whereas this is mu inverse 0. And then I impose a stability, etc. But then there's the GOB. So this is the definition of the Nakajima Quiver variety. And if you like, you're also, I can also define an extended version where the values of the complex moment maps are also regarded as part of the coordinate. So this is copies of C for each vertex. So for each vertex, there's a FI parameter, if you like, and those you regard as part of the coordinate. So this is the minimal definition of Quiver variety. Okay, so now I'm going to chiral the story, or going to discuss the BOA version of this story. How does it go? Well, basically it is actually very simple. So here, these are just the matrices, right? So, but I'm going to promote these matrices into fields of the BOA. That's the motto. So let's chiralize into BOA. Well, let's see. So the first ingredient, well, I'm going to emphasize the parallel with the Quiver variety story, although there are important subtleties which we'll come to. But first of all, before the reduction, it was just a collection of matrices. And then we have the simple ingredients. I'm going to define B sharp. So this is a BOA, defined from the data of the QBW. So this consists of several different ingredients. The first is the free beta gamma system. Free beta gamma system, and these are promoted to xi, yi. And yeah, I think alpha I, beta I, the counterpart alpha I, beta I. And except that these are, it almost looks like, okay, alpha replaced by I and j. Sorry, maybe this is not good notation. But the point is that these alpha x and y's are beta gamma ghosts. So what it means is that this itself, for example, it's a matrix. So it has a matrix index, yi, gamma delta, etc. And then impose the relation, like y, x, and y, w. So this is equal to, okay, so I need to write down the indices too, alpha beta, yi, w, gamma delta. So this is like a 1 over 1 minus delta, and there's delta ij. If you like, there are also contractible indices. So this is just a simple free beta gamma system. So for each arrow, you're going to associate the free beta gamma system. And for each arrows in the opposite direction, we have some relation like this. Now, you're going to write down something afterwards, but let me first proceed to the next ingredient. So this is the counterpart of this T star lep. Now, there is a counterpart of this thing, in this of the action of the group. So the action of the group comes from the fact that the Higgs branch has an action. And that comes from the fact, in physics language, that means that there is a Fravor symmetry. Now, when you have the Fravor symmetry, there's a background gauge field you can turn on. And if you go to the boundary, you get the vertex operator version of the algebra, which is the Kac-Moody algebra. So there's a statement is that there is a current of the Kac-Moody algebra, which you can write down. So at each vertex, U and I, so U and I current. And this takes actually exactly the same form as this formula. So you just promote this to fuse. I'm going to write down the same thing. xi minus 1 plus ji. And yeah, there are going to be corrections, but that's the idea at least. Okay, so that's the current. And then once you have the current, you can do the counterpart of the symplectic reduction. And in the BOA, there is a reduction procedure associated with the gauge group, which is this BRST reduction. So you're going to do the BRST reduction. Or if you like, if you're more mathematics language, it's a relative version of the semi-infinite cohomology. Well, semi-infinite means something like Dirac C. So, but in any case, there is a BRST reduction in semi-infinite cohomology, and that's what we're going to do. And in order to discuss that, first, you need to include BC ghost. Okay, so these are the BC ghosts. And then, so it's essentially the same commutation relation as this, and except that these are, of course, fermions. And then once you have the BC ghost, you can write down the supercharge. And there is a canonical formula for this, which is like exponential super I. And then there is this the current. So you combine all these currents. So let's call that JB star. And then there is a half times JBC, where this is the current associated with this thing. Well, the formula doesn't matter for this purpose, for this talk, but I can write it down. So there is some BRST operator like this, which you can write down. And once you have the BRST charge, which squares to 0, then you know what to do, which is to take cohomology. So that's BRST cohomology, or semi-infinite cohomology. and with respect to the supercharge. So that you can write, and in the mathematics notation, you write this as this thing, and this is the GLB action with respect to this vertex operator algebra. So that's this thing. Okay, I forgot whether to include the BC in the notation, but anyway, the meaning is clear. So you just add the BC ghost and then do the BRC reduction. That's the story. Except that there is some subtlety. So of course, for this BRC homology to work, you need Q squared to 0, of course. But the question is that, is this actually the case? There is already a formula, and I have essentially told you all the OPE, so you can just compute it. And it turns out that it's actually not 0 in general. So it's not 0. So you cannot define the BRC homology. Something is wrong. Now, there is actually a physical counterpart of the story. So I said that these 2D BOAs are the boundary theory of the 3D theory. Now, when you start with the 3D theory and go to the boundary, in general, there are anomalies associated with the boundary, which means that you have to cancel the anomalies and you need to incorporate. So that you can do by incorporating some extra matters localized on the boundary. And another way of saying that, purely BOA way of saying that, is that this Q doesn't square to 0, so you have to add something to make it 0. Let's see. Yeah, so more technically speaking, the JJ has a commutator, sorry, OPE, and OPE has a double pole, whose coefficient is proportional to the level. That's like a quantum effects, and that spoils everything up, because if you have a double pole, you want to take a residue. It's more complicated. In any case, you have to do something and add something extra. And in the physics discussion, so this is UN, and there is a UN part, and UN can be decomposed SUN part and U1 part. It is called the SU anomalies, the U anomalies. Now, what about the SU? Well, first of all, let's discuss the SU anomalies, SUNI anomaly. But as it is. And so what are the, let's say, anomalies? Well, for SUN anomalies, there is actually a way, well, first of all, the first comment I have is that there is not a unique way to cancel the anomalies. So you can have complicated thing, for example, complicated 2D theory to cancel the anomaly. And the choice is not at all unique. And depending on the choice, different choice, you get a different boundary BOA. However, you can also try to look for canonical or choices of canceling the anomaly. And there's one way for SUN anomaly. So this is canceled by incorporating, including boundary, 2D. Boundary means a 2D. Free fermion, fermion. So in the BOA language, it's like a fermion. If you're worried about supersymmetry, it's a fermion multiplet, fermions. And the copies, and how many fermions? How many fermions you need? There's a formula for that, which is that Wi plus Bi plus Bi plus 1 plus Bi minus 1 minus 2Bi. And yeah, so I'm going to write this as a W, so D equals to W minus CV, where C is a Cartan matrix. So I forgot to say that I'm going to consider linear quiver chains, although some of us are going to say generalized to more general quivers, etc. But let's say I'm going to discuss the linear chain of this type, and then C is the Cartan matrix. So this is the same expressions. Ni, sorry, where is Ni?
Yeah, I'm just confused. You have J sub UNI current.
Yes.
Your alphas and betas and so on are going from 1 to NI.
Sorry, yeah, indeed, sorry.
Is that VI?
Yeah, sorry, NI is VI, sorry.
Okay.
Yes, indeed, NI is VI, sorry, yes. Yeah, that's right. So, yes, thank you for asking. Anything else unclear? Oh, okay, there's another one there. Okay, so, okay, I see, in the anomaly. Oh, sorry, okay, in the blackboard, it's, if you're sitting in front of the blackboard, it's, okay, I see, good, thank you, yes. It's a bit hard to see when you're in front. Like that's a typical thing for a teacher. But in any case, let's see. So, well, first of all, you need to add this thing. So you need to assume that this is 0 or positive. When it's 0, it's called a balance. It's positive. You can cancel the anomaly this way. And this condition, if you know, is the same as the Gauss-Witten's good classification for good theory. condition for good theory. Okay, so what about the U1 anomaly? Now, for the U1 anomaly, there is one way to cancel, one minimal way to cancel it is to include the Heisenberg. Hi for each vertex, such that they have the OPE, I think you can see. So OPE is the HI is Z, is equal to Z minus W squared times Cartan matrix. So that way, that's the minimal way to cancel it. So actually, so we need extra ingredients, which is like a free fermion, DI copies of free fermions, which I might write 5 psi, for example, and then Heisenberg. So these are the extra data. So I emphasize the parallel with the Quiver variety, and that's inspiring. But also there are some subtle differences. You have to add extra ingredients. So even the defining data requires extra data. And then once you do this, you have to modify it, phi I minus psi I. And if I remember correctly, you have to put in the generator. So this is the identity component. So this is the matrix. So you write the diagonal part to be the Cartan. And so it's actually interesting because you see that this HI is like identity part. So this is an analog of the value, the chiral BOA counterpart of the value of the complex moment map. So let's see, there are extra subtleties, but the story goes well, and it works. Okay, so once you have this, you have a definition of the BOA. Now you can ask the question of how did it look like, right? So. Okay, I think I have 30 minutes. Yeah, not 20, right? So, oh, yeah. Sorry, it's like a 30 minutes or 20? Okay, 20 minutes, yeah. So, okay, so let's see. It's 20 minutes. So, okay, so what are the theories look like? Well, okay, then I need to speed up a little bit, but let's see. Nevertheless, I'm a down-to-earth person. So before coming to a general theory, it's nice to talk about a very specific example. And it's this theory. It's an example of a balanced quiver. Hope it's quiver, yes, 2. So for example, I can take a quiver of this type. Well, first of all, everything is explicit. So what you can do is to try to run the BRST charge, everything is explicit. So if you want to go to the BRST, well, of course, it's defined by BRST reduction. You need to find a nice operator which is invariant as BRST charge. So you can try to be hands-on and try to look for that. Now, let's see. So what is the way to look for that? Well, there are some operators which you can write down. Well, for example, if you take I1 itself, it's not at all BRST invariant. It has indices, and indices don't transform non-trivially. So you need a little bit more to make it work. Now, there is, for example, some canonical, let's see, at least method for trying to guess what the operators are. For example, you can start with this vertex. And first start with this I1 to go up, and then go to the left, which is like a Y1, and then go down, for example, J2, for example. Now, it's like going around the path, and it's a gauge invariant. So this is actually how we see the correspondence to the Higgs branch. So Higgs branch are parameterized gauge invariant operators, so this corresponds to path, right? So I just do the BOA version of the same thing and write down the operator like this. Now, you can also write down the same thing in the opposite direction. So you can also go in this direction. So that's like, okay, what I should do? First, okay, so if I want to, 2 from there, then I need to first I2. But then I need to take X1 and then J1. Or anyway, so maybe you're getting tired of indices. But in any case, it just simply corresponds to the path going the other direction. Now, you can try to go, for example, there is actually a similar one, but staying at one of the vertices. It can be, let's see, so, and then that's this one, J11. And in fact, this one is particularly simple looking, because this is also another path, which just going back and forth in between here. That's another cross path. So you might write out the formula like this. But actually, this itself is not gauge invariant. You need to add the Heisenberg contributions. which is the extra contribution. So the moral of the story is that if you have a coordinate on the Coulomb branch, you can more or less uplift it to the fields of the VOA, except that precisely because there are extra subtleties in the defining data, you have to correct it a little bit. But, sorry? Oh, sorry, did I say Coulomb branch? Sorry, Higgs branch, yes, sorry, yes. Higgs branch, yes. Well, of course, if you go to the mirror, it's a Coulomb branch, but yes, Higgs branch, yes. So you are in the yeah, these are coordinates. And now you might think that there are many other paths, but it turns out there is a momentum up relation, and so not everything is independent. It turns out that these all three are what's necessary. Now it turns out that if you have the three data. The interesting thing is that if you take this and take some appropriate combinations, it turns out that together with you need to add value of the fermions, etc. But in the end, you can map it to strong generators of the W-algebra of GL4 and the minimal nilpotent orbit. F minimum means the minimal nilpotent orbit of the W-algebra. And so this is okay. So this is not exactly so, but essentially by reshuffling the generators, and then we can arrive at the W-algebra. That we can check explicitly. If you look at section 5 of the paper, we have detailed computations, and then so there is a statement that in this particular example, there is embedding. Sorry, there is a homomorphism into the vertex operator boundary BOA we are starting with. Except that W-algebra is not everything. There are many other generators involving the fermions, etc. So this thing is even richer than this original W-algebra. Now, this raises many questions. Well, first of all, if there is a W-algebra, can you try to find some nice structures? Well, first of all, I didn't guess what type of W-algebras you might expect for a more general Quiver rather than this, for example. And also, for example, if there's something else here, then what you're going to it's not just a W-algebra, but something more. And how you study this? Well, in principle, you can have the fermionic generators and things like that, and that's actually what we tried. But the formula looks increasingly complicated, as is often the case in this BOA. So we need a systematic procedure. Now, in the remaining time, I'm going to try to explain that systematic procedure. And the idea is that, I would call it the localization of Quiver BOA. Okay, so what is the idea? Well, the idea is to try to appeal to the intuition between the geometry, the Quiver variety, and then there is a counterpart, this vertex operator. So this is BOA. So this is a Quiver variety. So it's a geometry. Now, the boundary BOA is complicated. But of course, the Quiver variety itself is also complicated. So the question is that, is there a way to understand it in a simple way? And this is a variety. So one of the procedures is that, well, you can go to a local patch. So this is algebraic. So if you take some polynomial, so this is defined by the region where polynomial is non-zero. You go to an open set into the Zariski topology, and then we are in a smaller space. And you can keep going to even smaller spaces, etc., and it becomes even simpler. Now, there is a counterpart of this in the BOA. So this is more like the ring of functions on this variety. So if you have this type of procedure, you can actually, there is going to be embedding into another BOA. And then you can keep going that. And at some point, you expect that the geometry is so simple that the procedure terminates at some point, and you have a free BOA. And if you take advantage of that, that means that the whole thing is embedding into free field. So you expect the free field realizations or Miura transformation and their generalizations. So this is the idea. Now, how to do that? Well, one of the systematic ways is to consider. So you need to do something at the BOA and apply the procedure of restricting the patch and things like that. And there's a very nice way of doing that, and that uses the idea of C4 BOAs. So you can consider C4 BOAs. Okay, so C4 BOAs, I'm afraid that I have no time to even remotely comment on that, but at least it's a sheaf, which means that for each open set, like this one, there is associated BOA and satisfies some compatibility conditions between the open set. And then you can define some C4 BOAs such that in some region, so okay, what is F? So this is like, and then you expect some simplification to happen. So you expect a C4 BOA. And let's see, and then once you have the C4 BOAs, you can, well, it's most strictly speaking, it's called the H-bar addict BOA because you have to you're taking the inverse of the fields. You have to worry about the convergence, which concept was introduced by Arakawa and collaborators. And then once you have the C4 BOAs, you can take a global section. And that defines some BOA. So this is a global section. And H-bar is not necessary, so I can set H-bar to 1. So this is the global BOA. And in fact, precisely because this one behaves nicely under this type of operations, you can show that this has a free field realization. Yeah, so let's see. So the statement. So the theorem, one of the theorems is that, well, so this algebra, here I don't need the H-bar. H-bar is set to 1. So this well, actually I consider M tilde, which is the extended quiver, which I defined earlier. And then this has embedding into beta gamma system. Well, in the language of this notation, you get the T star of C n slash M times some Heisenberg, copies of Heisenberg at each vertex. So there's a formula for n and m, but I don't remember it now, so I'm not going to write down. It's in a paper. So these are integers. And these are also levels, which you can compute a priori. And then these are like a Heisenberg. And then, so these are the beta gamma system. So that's one of the statements. And in fact, this is an explicit, well, it's not like an existence statement. There is a precise algorithm. So the procedure is that you're starting with a quiver. And then there's a procedure for eliminating that to make it a simple quiver. And they keep doing that. In fact, essentially, in the process, it's somewhat like a confinement, actually, that you remove the gauge node of the quiver. So in each process, you keep removing the gauge node of the quiver. At some point, there is no gauge group. So you get a simple theory. BRC reduction becomes trivial, and you get something like this. And you can work this out very explicitly. And then, for example, in some examples, you can show that, for example, in the examples we discussed before, where there is a W-algebra, you can apply this procedure and then try to see what type of field realizations you get. And it turns out that that's what you get from the Wakimoto free field realizations. But this one is much more general. So you can do a variety of quivers and very systematic procedure for writing the free field realizations. Okay, yeah. So that's the thing. But now I have just a little bit of time, so let me try to fill in one missing point, actually, in this discussion. So here, it's actually, you notice that things are subtle. The reason is the following. So okay, I declared that I was interested in studying this BOA, right? So that's what we wanted to study. And then I say I invoke the gadget. Yeah, so this is, yeah, so there's C4 BOAs. And define some D. And it has a nice free field realizations. But a priori, this D can be different from this B, which I wanted to study originally. And yeah, it's actually a very subtle question. So, so the difference is that here, I take a global section first and do the BRC reduction. But here in this business, you first do the BRC reduction locally, and then take a global section. And there is no guarantee that they commute. So they might not be isomorphic, for example. And so the question, there is a question hanging around that what is the relation between the two? And we certainly don't know the final answer. But at least there is one particular statement we're going to show in the second version of the series, which is this math paper. So this is a theorem. So there are two assumptions. Assume, well, first of all, I defined previously that di equals to wi plus bi minus 1 plus bi plus 1 minus 2bi is 0 or positive. So this is a good. I still keep assuming that. And then one of the following. And so these are the various different cases of the quiver. So for example, one is that the quiver is totally negative. So it means that the Q is complete. And so the Cartan matrix is negative, if you like, but complete and two self arrows at each vertex. So this is one case. Yeah, you can have, for example, two nodes, for example, and then there should be at least two nodes, two arrows here. It's a little bit weird one, which you usually don't encounter in physics, I guess. But and then it's a complete graph, so it's connected, something like that. Now another case is the dinking. Well, dinking I'm still assuming that it's a linear quiver, and or another more way of saying that is that it's almost the vertices are almost abelian, except at 2 points. Or maximally 2 points. So it includes the well, let's see. Actually, Q is and then another is A1 quiver, and another is the Jordan quiver. So these are the technical requirements in order for the proof, and then the result. Yeah, so this is also a theorem in a paper. And another theorem in a paper, this is by us, Z, is that there is a, so, well, first of all, there is you can show in general, there is embedding into this CIF version of BOA, the global section of the CIF version of the BOA. So there is always a homomorphism as a vertex superalgebra in between the two. And this is injective. Oh, sorry, I wrote the theorem. Sorry. Okay, I don't need to. Okay, maybe I should write it here. Then injective. We also have a related result about the vanishing of the negative part of the cohomology. But let me not write it now. But at least you can show that this map is at least injective. Now, once you have this, you can try to make the loose end, because first of all, originally you might be interested in this, but that's embedded to this CIF version of this, which now has a free field realization. And if this is injective, so this becomes embedding. And then this part is also embedding. And hence, you have a proof that's embedded into the free field BOA. So you have a free field realization of this guy. Yes. Now, I have 5 minutes, so I can comment a little bit on also the connection to the W-algebras. Yeah, so, well, as I said at the middle, we have a connection of these two W-algebras in some cases. But now the W-algebras themselves are not these boundary BOAs. So in some cases, there is a morphism. But it's actually not necessarily easy to say in general whether it's injective or surjective. But first of all, but sometimes, for example, if you go through this bit, so this has a free field realization, so you already have this algebra. So you can just go ahead, and then this is mapped to the free field. And then you can check what type of free field realization you get. And in some cases, it coincides with the free field realizations known in the literature. In which case, we know that it's embedding. So in that case, there is also injection. So you can make a connection to the W-algebra. And okay, so which W-algebra? Well, to properly explain that takes more minutes. But there is a class of Quiver gauge series which goes by the name of T rho sigma theory in the notation of Gauss-Witten. So in particular, the Higgs branch of this theory is a nilpotent cone associated with the transpose law intersection with the Slodovitz size for sigma. And in this case, and in particular, for example, when this sigma is 1, 1, 1, so these sigma laws are partitions of n. And so when this is the case, well, and then you have the sigma only, and then there is an expectation that you get the W algebra associated with this nilpotent element coming from the sigma, and then you get the level Wn minus 1. Not a critical level, it's a little bit off, but there is a W algebra map into the vertex operator algebra. So there is still a connection to W algebra. We know in some cases, and we have some non-trivial checks for that. Now, I'm going to finish by saying that, okay, so this is a subalgebra. So, well, okay, I haven't checked that it's actually embedding in general, but sometimes it's a part of the story of the BOA, not everything. And, well, in that case, and so you can naturally imagine that is there any way to characterize this subalgebra inside this BOA? And I don't know the answer. I don't know the answer, except that there seems to be some connection to nice mathematics known as the Namikawa-Weil group. So this is related to the resolution of singularities, deformation of the symplectic resolutions. And in that story, Namikawa have a nice story where there is some version of the Weil group acting on the geometry. And you can talk about the similar version of that on this geometry. And so in that case, as far as I know, I don't claim to know much about it. But as far as I know, it's a permutation. And then, so the natural expectation is that the image of this is in the fixed point set of this thing under the Namikawa-Weil group. So it seems that there is some more story to be clarified, and along the way, the study of the geometry itself could play some important roles. So I guess my time is up, so let me finish. Thank you.
Hi. If I consider the D3 NS5 brane, D5 brane construction for this Gauss-Witten theory,
Yes.
What's the 2D boundary modes come from? Like this Heisenberg algebra and this zero coming to Fermi multiplet?
That's a boundary condition, so you have to, it's extra ingredient which you need to add. So it's not 3D theory degrees of freedom, but extra degrees of freedom localized on the boundary. Now, so for free fermions, you just include a Fermi multiplet. So that's a multiplet in 2D, preserving half the supersymmetries. Now, if Heisenberg, okay, so it's Heisenberg, it looks a little bit artificial, but you can also, if it's fine to add extra U1 current, you can also realize them by free fermions on the boundary. So the short answer is that it's not a part of the property of the theory, but it's more like a property of the boundary condition. And you need to, yes?
You have some description of your theory from like 10 dimensions or whatever,
Yes.
then reducing should give you also the boundary condition.
Yeah, I mean,
So as I think the question is, how do you learn that boundary condition from this reduction?
Well, let's see. I mean, here it's, I mean, let's see. First of all, it's not unique. You can have different boundary conditions as long as it's compatible with the A twist, and for example, consistent with the supercharge, it works. So it's not, first of all, it's not a unique choice. That's comment 1. And the comment 2 is that, okay, but if you're still looking for some nice interpretation, for example, well, you can, depending on whether you can go to 4D or 6D, et cetera. But let's say you do go to 4D. And then one way is to go to a cigar, 4D cigar. And so instead of having, so we have a 3D theory on the interval, right? So if you suppress the 2 dimensions, it's a boundary condition here. And then you can start with the, so this is a 3D theory. But you can go to the 4D theory on a cigar with omega background turned on. And then you can discuss the BOA at here. And in that setup, so that's just a 4D n equal 2 series omega background. And there's a nice paper by Yagi and G1O, which says that actually the setup is the same as what the Rasteri, Beam, and others do in the connection with constructed chiral algebra from 4D theory. So in that case, that's just omega background, you reduce it, that's it. And in that case, actually, but there are important differences actually, because in that case, okay, what happened to the choice of boundary condition I have been talking about? Well, it's related to the fact that, first of all, in that case, people typically are interested in superconformal case in 4D. It's called a balanced, in this language, it's a balanced quiver, so there is no need for extra matter. Also, they're doing SUN gauging instead of UN, for example, so they don't care about the U anomaly. So because of these reasons, you don't really have to worry about it. The canonical choice is almost empty. And then that's how you get the boundary BOA in our case. But so you can sometimes go to 4D, but our discussion, at least as the defining data, is much more rich.
So Nakajima Quiver varieties are famous for being hyperkähler. Does that mean that this vertex operator algebra is some kind of n equals 4 superconformal algebra?
Let's see. I see. Yeah, I mean, it could be. Yeah, indeed, the boundary conditions are 0, 4, for example. So it's consistent with supersymmetry. So.
Large or small n equals 4 superconformal algebra?
Yeah, that I need to think. But if I have to bet, well, it's fun if you get a large one, but probably not. But if I have to bet now. But yeah, but I think that's interesting, yes. And indeed, probably because I have so far really touched on the fermionic part of the direction and then defined the W-algebra. But then you have to, fermionic parts, you have to.
Yeah, I mean, it has to depend on how you cancel the anomalies. You could cancel the anomalies in some way that doesn't have anything to do with n equals 4.
Mm-hmm. That's right, yeah. So I think the hope is that at least this is a kind of, there is a, Heisenberg, et cetera, it's a kind of most minimal way of canceling the anomaly. So in that case, you might have hope of having larger supersymmetry, yes. As you say, in general, we can have anything with a lower supersymmetry. So yeah, probably it's too much to hope for that supersymmetric version of this. But I think it's an interesting question. Yeah, I don't know the final answer.
If you have n equal 8, then you can, if you have n equal 8, then the boundary algebra will have
in a special case, yeah,
a small n equal 4.
Yeah.
I don't n equal 6.
Yeah, interesting. Yeah, I think. Yeah, thank you for asking. I really should look into that. Yeah, I mean, so far we have the very computation, very simple examples, very explicit and in general argument. So, but a lot of examples are yet to be explored. So, I think there's room for further discoveries.
Question in the back.
I just wanted to know if you have any counterexamples to this injectivity.
Subjectivity here.
No, to injectivity, do you have any counterexamples?
For injectivity, not that I know of. At least this one, right? So yeah. Let's see. Was that the case? Yeah, I think. Yeah, I mean, there is some counterpart of some statement in the Arakawa's paper, but I don't remember if it was this statement. But yeah, I need to check. But I believe that there is no counterexample. I can correct it if I. Yeah. But it's somebody else's paper, so I don't claim to read it too well. But yes, yes.
I didn't mean that one. I meant the horizontal one.
This one.
No, not this one. This one.
Oh, horizontal one. Yeah. Oh, sorry, this one, right? So, yeah. When I meant that, yes. When I defined it, yes.
So if there are no more questions, let's thank the speaker. And the next